Well, I bet everybody wants lunch now. It's difficult to be the last presentation of the session. I hope I'll manage to catch a bit of your attention. I don't know. This presentation, well, does not have like estimators. It concerns source coding or like Shannon theory of certain measures which have some geometric structure. Okay, so I sort of want to motivate later why these rectifiable measures, which appear in geometric measure theory and stratified measures that I defined here, are maybe logical things to consider. But first, in fact, I want to start by just talking about like why, I mean, something that should be obvious, that like measure theory is like the good language to talk about information theory. And then maybe try to introduce for, I guess, most people here some ideas from geometric measure theory, and then try to talk about the stratified measures. So I'm going to deviate a bit from what's in the proceedings. This is more like the motivation of what I put in the proceedings, because, yeah, well, there is a very technical result at the end of the proceedings, so I don't want to talk about all the notation. So measure theory, in fact, well, it was introduced just to explain integration. So there's a lot of people like Lebesgue, Borel, Fréchet, but it was Kolmogorov already in 1933 that realized that this language was like the good language also to understand probability. So that then you could have this perfect analogy between integration, which is like a linear operation on functions, and expectations, with like a linear operation on random variables. And well, I don't know how familiar people are here with like measure theory. I just want to like define certain things so that like they are not just completely like garbage words. So in measure theory, you'll have like a set E, and from that set, you're going to consider like a distinguished class of subsets, because it was realized very soon by Hausdorff that in general, you can't define a measure consistently on all subsets of an infinite set. So this is like a technical thing. So you distinguish a class of subsets, which you call sigma algebra. Normally something that contains all the open sets of a topological space, for example, if you're working with topological space. And then a measure will be a function defined on this class of sets that assigns to every set a positive number such that the empty set gets 0, and such that every time that you have this joint union, the measure of that is the sum of the measures. So it's something that works like the area of the volume. And this measure is called sigma finite if you can divide the space, the set E, into a countable number of pieces, all with like finite measure. And of course, a probability measure if the total space is, the total measure of the space is 1. And this is particularly important for us. There's this property of absolute continuity, which says that, okay, you have a measure rho, which is absolutely continuous with respect to mu. If you can always compute the measure rho as an integral with respect to mu of a certain function f, and this function f is what is called like the density of rho with respect to mu. So it's like the Radon-Nikodym derivative of, so it's like a density function, okay? So in fact, then you can write very generally this asymptotic equipartition property for, like, let's say memory-less sources, like IID samples. Because you start with a measure space, you suppose that mu is sigma finite. So that's important. The reference measure has to be sigma finite. But like most of our favorite measures are. So the counting measure is sigma finite, and the Lebesgue measure is sigma finite. And then you consider probability rho, which is absolutely continuous with respect to mu, and has density f. And then what this theorem says, I mean, I'm not claiming any novelty in this, but you never see it written in this generality anyway, is that if the entropy is finite, so the entropy is just the expectation of minus the logarithm of the density. If this is finite, with respect to rho, okay? So if this is finite, then this set, which is a set of typical realizations of rho, I mean, maybe I'll explain why this, concentrates most of the probability. So here, this tensor n means I'm taking IID samples. And the volume of this set is sort of lower bounded and upper bounded by something that is like the exponential of n times the entropy. These typical realizations, you can think of them as, well, those such that this quantity is close to this quantity. So this is supposed to converge to this in probability because of the law of large numbers. So you can distinguish like this high probability set on which this will be close to its expectation. And then the other ones, well, you just neglect. So the well-known examples is in the Cover and Thomas and all that, is that you take a finite set and you take mu, the counting measure, and then this is just the probability mass function of the counting measure. So the entropy is just a discrete, so it's a discrete entropy, it's Shannon entropy. Then this mu tensor n is also the counting measure. So this bounds that I showed before told you that the number of typical realizations is something that exponential of n times the entropy. Of course, this is already in part 1 of Shannon's paper. Then a second example is like you take RD, and then you take as reference measure the Lebesgue measure, corresponding dimension D Lebesgue measure, so just D volume. Then this will be a probability density function, because now your rho, being absolutely continuous with respect to a Lebesgue measure, is what we call like the law of a continuous variable. So it has a density function. And this is differential entropy. And now what the inequalities before are telling you is that the volume of the typical realizations of this rho is approximated by the exponential of n times the differential entropy. Okay, so here I will already make a remark of what this pointed to. It could happen that rho tends to concentrate, maybe still absolutely continuous with respect to the Lebesgue measure, but let's say is very close to be concentrated on a line or a surface or something that is not dimension D but lower dimensional. So in that case, the entropy will be very small. So it will go to minus infinity. So, and this is consistent with this estimate, no? Because it's like the volume of the typical realizations will sort of live in a lower dimensional thing. So this has to be close to minus infinity to sort of be consistent with that volume estimate. So the divergence of the differential entropy to minus infinity is consistent with this like volume estimates. In the limit, if it's minus infinity, the law is singular. And it means that the volume is 0. You know, it's like it has to happen. Okay, but that will be relevant for what we'll talk later. But maybe even before talking about geometric measure theory, which is maybe scary and complicated, I wanted to present like the idea of stratification in this most elementary way. So there is a third elementary example, if you want, that you could consider. Is a probability measure that you can write as a convex combination of one that is absolutely continuous with respect to the Lebesgue measure and another that is discrete. So is absolutely continuous with respect to the counting measure on some countable set S. Now, you can prove, I mean, in one line, that this measure rho then is absolutely continuous with respect to the sum of these two measures. So the sum of the Lebesgue and the counting measure. So you can compute its entropy because it's absolutely continuous, it has a derivative, and you compute the entropy. So it's a little lemma to show that in fact the entropy has this funny expression. So is the entropy of Q, just like a parameter if you want, so it's Q log Q minus Q log Q minus 1 minus Q log 1 minus Q, and then Q times the differential entropy of rho 1 minus 1Q the Shannon entropy of rho 0, which is like a discrete variable. So you have this expression. But then the question, of course, because I mean this is just expression, but what does this mean in terms of the asymptotic equipartition property, or in terms of, let's say, like the more concrete like coding properties that we want? And in fact, if you want to think about that, well, there's like a little trick. And the little trick is to say, okay, let's consider in fact that these measures, rho 1 and rho 0, in fact have disjoint supports. Because the rho 1, being continuous, sort of doesn't really see the set S. So I'm going to use a set E0 which is S, and E1, which is the complement of S. And then rho, you can suppose that in fact it's defined on E1 because it ignores S. And now there are these, you can partition now the product of the set, the initial set, not the set EX, RD, into this strata, okay, where like these are, all these factors are either E0 or E1. So they are parameterized by these words, okay, now these are binary words. And now the product measure can be written as a sum of this form, okay, this is just, you multiply. But the remark now is like, okay, these weights that are associated to every binary word are precisely like the when you put together all the words that have the same number of ones, they give you a binomial distribution. So that now you can say, okay, this y is, well, this is not quite true. I mean, this y is a vector of Bernoulli variables, but now when you consider all that have like a given number of ones, that is binomial in Q, and then so that given number of ones will concentrate around in Q. That's what I wanted to say. Okay, so somehow you can ignore many of the realizations and just retain those typical ones. Okay, and for those, there is like a stratum, you know, like when you restrict, so you restrict this sum to those, and now these probability measures here are going to be supported on the corresponding stratum, but for these typical realizations Y, this stratum will have dimension NQD. It won't have just any dimension, it will have dimension NQD. Something roughly that. So basically the way of understanding the chain rule is like, okay, you know, because before we had the chain rule, and now I just wrote it in exponential form. So this part is approximating the volume of all the typical realizations of rho. This part is approximating the number of typical Ys, or that we could call like the typical strata, the strata that we have to retain if we want to do the analysis correctly. And this, well, you could see in this conjecture that is the volume of the typical realizations that fall in each one of these typical strata. So, and this, of course, is something that you have to prove, and that I proved. It's a bit more delicate. I mean, the statement is not as neat as that, but you could look at the paper. But it's almost that. And then there is like a funny connection. Well, I don't have that much time. It doesn't matter. I will finish in time. So there is a funny connection with the Rényi dimension, because Rényi, in fact, already had considered these discrete continuous mixtures, and any measure, in fact. So he had this device that he could take any measure, define an RD, discretize RD in little cubes, compute the entropy of the discretized thing, and then said, okay, if the entropy of this discretized thing grows as d times log n plus a certain constant plus something that goes to 0, then I'm going to call this the dimension of the measure, and I'm going to call this the entropy of the measure. So of course this coincides in the continuous case and in the discrete case with what you would expect, but also he computed that when you have a mixture, then this dimension is QD, and the entropy in this sense is this thing that we found with the chain rule. So somehow this is giving a new explanation of a more geometric explanation, because it's purely analytical, of why this dimension is QD. It's somehow like the dimension per symbol of this typical strata, because the typical strata had dimension in QD. And this, which in Rényi's case does not relate to any sort of geometry, now is giving you some quantification of the volume of the typical strata. Okay, so that's concerning stratification. Now, concerning geometric measure theory, probably I won't say much because I have 5 minutes, but the idea is that when you look at the general statement, precisely you have all these measures that maybe are not continuous, are not discrete, because they sort of live on something that has some intermediate dimension. So maybe they live on a line, or they live on a surface. So, okay, you could think, okay, maybe a measure that lives on a manifold. But the problem with the manifold is like a manifold is not a measure theoretic concept. You have to care a lot about like differentiability and all sorts of stuff that is not really relevant for our purposes. So it turns out that the good language is this language of rectifiable sets, which are almost C-web manifolds, but up to some defect that you can introduce, which is negligible most of the time. So the good reference measure in that case is the Hausdorff measure, which is somehow built by approximating. This is an illustration of how you get the H1 measure, so the one-dimensional measure, where you approximate it by little balls and diameters of little balls, and then you get the length of the line. But you can do this in any dimension. So in fact, for any m, for any real m positive, so this gives you a notion of n-dimensional volume. And then in geometric measure theory, the role of manifolds is played by these rectifiable sets. So the rectifiable sets are images of bounded sets under Lipschitz maps. Okay, so an M rectifiable set is the image of a bounded subset of Rm under a Lipschitz map. And then you can do countable unions of that, or even countable unions up to some defect that has Hausdorff measure 0. So of course, the sets I introduced before, this E0, E1, which was S and RD minus S, are rectifiable. So a countable set is a countably zero rectifiable set. RD is countably derectifiable because, I mean, you just divide in little cubes and each one of those is derectifiable. And an m-dimensional C1 manifold is countably m-rectifiable too. In fact, yeah, there's a more complicated result that every rectifiable set is a subset of the union, a countable union of C1 manifolds, and a set that has HM measure 0, okay? And for all the purposes that I'm going to cover in the next 2 minutes, this HM null set is irrelevant. So you can just forget it. And this is, okay. And so I have 2 minutes, so 1 minute for this beautiful result by Marstrand, which said that if you have a locally finite and regular measure, and you take any non-negative real number, and you compute this local density, so you look at the measure of a ball, and you divide it by the measure of the ball under the Lebesgue measure, and you quotient that, and you take the limit. This limit exists, and is strictly positive and finite, so if this exists and is strictly positive and finite for almost every x, then S has to be an integer, which is a crazy thing. This is Marstrand theorem. But later, Price in the 80s proved something even crazier, which is it's not only this has to be an integer, this measure has to be rectifiable. So being rectifiable means that there is a rectifiable set, and in the very formal notation introduced before, it's called like countably HM rectifiable set of RD, such that this measure that has a well-defined density, in fact, is absolutely continuous with respect to the Hausdorff measure restricted to this rectifiable set. Somehow, the measure lives on that rectifiable set. And remember, this rectifiable set is something like a countable union of like manifolds. Okay? And in fact, yeah, and the study of this from the point of view of like information theory was already done in 2016. So somehow the idea here, and I will skip this because it's sort of technical, is to introduce these stratified measures, so I have 30 seconds, which are convex combinations of these rectifiable measures. So this is like a natural generalization of these discrete continuous mixtures that I showed before. And in fact, you can play the same game. So when you do products, you will have this sort of funny sums. Now, these will concentrate around its mean, so you can restrict this sum dramatically to a very narrower number of like terms. And then for the restricted sum, these things are going to leave on certain strata whose dimension concentrates around m times the mean dimension. And this is what it was at the end. So the dimension of the typical strata concentrates around n times this like mean dimension. So somehow, yeah, you can play again this game that I play for the discrete continuous mixture. Well, thank you very much.
Thank you, Juan Pablo. Is there any question before we go to lunch? Yes.
Yeah, so I had a bunch of questions, but I will try to limit myself so everybody can go to lunch. So the first thing that so given that you have a general measure, you know that its components are like discrete, like in the dimension spectrum, let's say. Can you do like some sort of principal components analysis on the dimension to get which parts of the measure are of each dimension?
I'm not sure I understand.
I mean, you have a measure, you don't know what it is, okay? You just have some abstract way of evaluating it. Can you decompose it in a simple algorithmic way into the parts that correspond to the dimension that must be from 0 to n from the Master theorem that you showed?
I'm not sure. I mean, I'm not sure that you can use this to do that. I do think that, for example, that from this perspective, and this is something I wanted to mention, all the measures that have the same average dimension, because I said that there is this sort of average dimension of the, because it's a convex combination, so you will make the convex combination of all the dimensions that you have. All the ones that have that same dimension somehow asymptotically behave similarly, in the sense that the realizations will sort of live on a strata that have roughly n times that dimension. So maybe this is not like fine enough even to, I mean, yeah, I would say that the problem of given an arbitrary measure, deciding if it's a stratified measure as a statistical problem, yeah, it's like a different problem than what I was trying to address here. But this is maybe something that is telling you how you would compress a measure if you know that is of that kind, because then you could project it to something that is lower dimensional around this typical dimension. So this is maybe a slightly different question. Yeah.
Okay, thank you very much. Let's thank the speaker again. Let's thank all the speakers of this session.